Welcome to a screencast that will provide an introduction to heat, enthalpy, and thermochemical equations. Let's start by considering a kind of fun reaction. This is the reaction between sucrose, C12H22O11, and potassium chlorate, KClO3. And if we take a gummy bear, which is mostly sugar or sucrose, and drop it into molten potassium chlorate, it undergoes a very vigorous reaction. You see flames, it gives off a lot of heat, and it produces carbon dioxide, water, potassium chloride, and an awful lot of heat. Now, a not quite as fun process that we could also consider is taking ammonium nitrate solid and adding it to water and allowing it to dissolve. And when it does that, it makes ammonium ions and nitrate ions because ammonium nitrate is soluble. And the temperature of the solution that's made goes down quite a bit. This is a reaction that is actually the basis for some chemical cold packs, where the surroundings get cold when the reaction takes place. Now, let's look at some of the details here of these types of reactions. Well, first of all, the fun gummy bear combustion reaction. That one produces carbon dioxide, water, and potassium chloride as products, but it also produces a fair amount of heat. And so we can treat heat as a product of reaction. It actually is a product of the chemical reaction. And this is what's known as an exothermic reaction. It's a type of reaction that gives off heat when it occurs. Now, conversely, the ammonium nitrate dissolving process, that one absorbs heat. Heat is taken in from the surroundings to allow the reaction to proceed. That's why things get colder, because energy is being absorbed from them. And this is an example of what's called an endothermic process. This is one where heat is taken in or absorbed. In chemical and physical processes, not only do the reactants change when they make products, so the atoms that are bonded together change how they're bonded, there's rearrangement that occurs and new substances are made. Not only does that happen, but there are also energy changes that take place. So in an overall chemical or physical process, energy is either given off or taken in, and that's an important thing for chemists and chemistry students to pay attention to. How we describe the energy or heat aspects of chemical reactions is using something known as enthalpy, symbolized by H. And enthalpy changes, or delta H values, are what we use to describe the heat of chemical reaction, the amount of energy given off or taken in. And if we tie that in with the balanced chemical reaction equation, then we have what's known as a thermochemical equation. And in just a moment, we'll do a couple examples of that. First of all, though, just a quick technical note. Enthalpy is technically heat flow at constant pressure. Now, we don't always do this, but we often do reactions with constant pressure, like on a lab bench. And if we don't, the differences between constant pressure and not constant pressure are usually reasonably small. And so, for our purposes, we can roughly equate delta H values, or enthalpy changes, with heats or energies of reaction. If you go further in chemistry, then you may take some pains to be careful about the differences between energy and enthalpy, but we're not going to worry too much about that right now. We're going to just generally describe chemical reactions in terms of enthalpy changes. Okay, well, let's start with a reaction, the complete combustion of butane. And butane is C4H10. And when butane undergoes reaction, it combines with oxygen. It makes carbon dioxide and water. Should be able to write and balance the chemical equation. And the new thing that's added here is that when 2 moles of butane reacts with 13 moles of oxygen to make 8 moles of carbon dioxide and 10 moles of water, 5,757 kilojoules of energy is given off in the process. So it's a product of this reaction. The other way we can write this equation, this thermochemical equation, is the reaction equation as before. C4H10 plus O2 makes CO2 plus H2O. And then the delta H value is written after the reaction. And in this case, we write delta H, or enthalpy change for the reaction, is equal to negative 5,757 kilojoules. Note it's the same value here as we have in the previous way of writing the reaction equation, but in this case, this value is explicitly written as a delta H, and the negative sign means that it's an exothermic reaction or heat is given off. So, important distinction, if it's a product, then we do plus. We write it on the right-hand side because this amount of energy, just like there's 8 carbon dioxides and 10 H2Os, there's also 5,757 kilojoules of energy as a product. But if we write it as a delta H, then we write it separately from the equation, but in the same line typically if there's space, and then we write delta H equals negative 5,757 kilojoules. If it's exothermic, there's a negative sign. Okay, another example. Dry ice, or carbon dioxide, but frozen, solid carbon dioxide, undergoes what's known as sublimation. It directly turns from a solid into a gas. And for it to do that, it absorbs 25.2 kilojoules of energy to take 1 mole of solid carbon dioxide and turn it into carbon dioxide gas. So here, the heat is a reactant, so we write it on the left side of the equation. And if we were to write this in the other form as a thermochemical equation, then we would write the reaction equation, or in this case physical process, CO2 solid makes CO2 gas, and then after that we write delta H equals 25.2 kilojoules, and here, because energy is taken in for the process to happen, that has a positive sign. And in general, for endothermic reactions, or in this case an endothermic process, the delta H will be positive. So again, either of these two ways are acceptable ways of describing the reaction process, but we most conventionally will write the reaction equation followed by the delta H as our thermochemical equation. Now let's do another example, but let's take into account some calculations and how we deal with not having exactly the number of moles in the process undergo a reaction. So, for example, what is the enthalpy change if instead of 2 moles, we have 5.78 moles of butane that undergoes a combustion reaction? So what's the enthalpy change and what does it mean? Well, there's our reaction equation. And what we know from this is that if we have 5.78 moles of butane, from the reaction, we know that when 2 moles of butane reacts, 5,757 kilojoules of energy is given off. So there's, for every 2 moles of butane, a delta H of negative 5,757. This is a stoichiometric conversion factor, just like we've used before with quantities of substances. And we set it up so that the units we want to convert from cancel out, the units we want to get to are left, and then when we do our calculation, we get negative 16,600 kilojoules. And then, of course, the interpretation is that when 5.78 moles of butane undergoes combustion, 16,600 kilojoules of energy or heat is given off. Another example, what's the enthalpy change if we have 63.9 grams of CO2 that sublimes? And then what does this mean? Well, as before, there's the thermochemical equation. And starting with 63.9 grams of CO2, to be able to use this enthalpy change, we need to know the moles of carbon dioxide. So if we're given grams to start with, we have to convert to moles. That should be a familiar process. And then once we have moles, then we can say, oh, well, what we know is 1 mole of CO2 solid takes 25.2 kilojoules of energy to sublime. And that's our stoichiometric conversion factor, but now involving the enthalpy of reaction, or the enthalpy change for this reaction. And once again, we're canceling units that we want to convert from, moving towards units we want to end up with. And this gives us plus 36.6 kilojoules. Positive value means energy is taken in. And so for this case, what this means is to sublime 63.9 grams of CO2, 36.6 kilojoules of heat would need to be absorbed. Now, as just sort of a summary of what we just did and kind of a moral of the story, a couple things to mention. One, chemists use enthalpy change, delta H, to describe heat of reaction, or heat of chemical or physical process. And enthalpy changes, the amount of heat given off or taken in during a reaction, is proportional to how much reactant is used and how much products are formed. And we can therefore perform stoichiometric calculations for heat or for enthalpy change in exactly the same manner as we would for amounts of substances. So everything you hopefully learned about chemical stoichiometry and calculations applies now to heats of reaction as well. And that's it for the introduction to heat, enthalpy, and thermochemical equations.